My name is Cody Davis. I'm a senior manager of distribution and grid mod at Electric Power Engineers. I've been here about 3 years leading a bunch of different grid mod and control initiatives and planning. Prior to that, I was a utility planning engineer at Ameren, Illinois for about 6 years. So I've got a good kind of mix of perspectives from maybe some different approaches from different stakeholders. As you mentioned, today we're going to do a brief intro to some of these topics. We're going to dive into 3 kind of core pillars of DER planning: forecasting, hosting capacity, and non-wires alternatives. So first, kind of baselining, what is a DER? Solar is the most common one, but the term kind of encompasses a whole bunch of different technologies. Things like wind turbines, energy storage, CHP, combined heat and power falls under there, but also things like EVs, managed charging, grid interactive buildings. Basically anything that is injecting energy or modulating its demand in response to different controls, price signals, et cetera, has some legitimacy as a DER depending on what you're doing. When we talk about planning with DER, really the core goals are similar to basic distribution planning, right, with some extra flavor. So first, we want to understand and prepare for the future. We want to be able to meet customer needs in a timely and efficient manner. Who does distribution planning? Everybody that owns distribution infrastructure. So investor-owned utilities, municipal utilities, cooperatives, campuses, large buildings that have their own components of this. Everybody has a piece of distribution planning if you own a distribution system. DER impacts specifically are driving changes in distribution planning processes, new outputs, new inputs, new complexity. We are increasing the visibility, the scrutiny, and the importance of distribution planning to the outcomes that impact customers, more than they've ever been in the past. Things are also getting significantly more complicated because of all of the DER and the choice and the new factors kind of coming in. So it's more important and it's harder to do well. So we have to kind of account for these things as we go. So again, 3 kind of core pieces of this. Forecasting is the process of figuring out what I should expect to happen in the future so that I can plan accordingly. This is estimating your future adoption levels of different technologies, as well as the actual impacts that those have to the system, right? So is it charging at peak? Is it charging off peak? Where are we getting injection? All of these, the actual impact and the timing makes a big difference, as well as just kind of how fast they get adopted. So those are both key pieces of forecasting. When we talk about hosting capacity, this is the phase of identifying where your constraints are for load or generation, and helping to facilitate the application process so that folks who want to connect new resources know what to expect and know how to find and identify good sites. And then finally, non-wires alternatives is about a new way to solve old problems. So leveraging DER, not just as a thing that's coming onto the system, but as a resource to help you solve problems efficiently and to mitigate system needs. So those are the 3 pieces. We're going to dive in first in forecasting. There's a lot of different aspects of forecasting. I'm actually going to start at the bottom. The most important thing to start with is the why. What do you plan to use the forecast for? That will inform all of the other decisions that you make above, right? So we have geospatial granularity is a really important piece, right? How far zoomed in or zoomed out do I want to be? Do I want to be at the system level, at the utility level? Do I want to look at individual customers? Do I want to look at feeders? These are all options, and they're all useful in different contexts. DER type is pretty straightforward. Which one are you looking at in potentially multiple scenarios? Time horizon is another big one. How far out do you want to look, right? Traditional distribution planning is 5 years. Emerging best practice is closer to 10. For policy objectives, you usually want to look even further out, right? So how far out you look is an important choice based on what you're doing. And then finally, temporal impact, right? How does this thing actually impact you at the time? You have some resources like solar that are weather-driven, that are kind of going to do what they're going to do. Not a lot you can do about it. You have other resources that are driven by market economics, things like battery storage, demand response, that are harder and more complicated, but still really important to capture. So when we talk about geospatial, system-wide forecasts are kind of the classic. This comes up a lot. This is either at the utility level of adoption or at the state level, sometimes at the regional or the ISO level for like how common some of these things are. Usually used to help kind of identify overarching trends and help kind of influence policy decisions and make ready. Useful, but not as specifically in a distribution planning context. Usually kind of an important background piece to when we're making distribution-specific choices. The flip side of this is the highly localized propensity modeling type of forecast. This is going into the individual customer level of how likely is this customer at this address to adopt a new EV or to adopt solar, and then using that kind of customer level analysis to build up from the bottom a more like system level or a more aggregated trend. So you're looking at individual customers, their likelihood to adopt, and then that kind of rolls up into this S-curve, like fast diffusion model or like a logistic adoption curve where it's kind of exponential on the early end, and then you start to reach that sort of bend carrying capacity, and it starts to taper off as you kind of hit that saturation point. So in my view, I'm a distribution planning engineer. Ultimately, what I usually want to get to is the mid-range, right? This is at the feeder level, at the substation level, where I'm doing my planning analysis, where I'm doing my investment justification, where I'm trying to figure out what's going to happen for my substation transformer. This is usually either gotten to kind of as a disaggregation of the system level data, right? So this feeder is going to get X percentage of the system-wide growth, or as an aggregation of that bottom-up data. So if you have customer level data, you aggregate it up to kind of get to that feeder or census tract level. And that's, again, that's what feeds directly into forecasts, analysis, scenarios, identifying constraints. This disaggregation process is messy and complicated, but generally, again, you're trying to get from the system level and then allocate down to individual feeders, or start from the customer level and roll your way up to that feeder level as kind of that aggregation. And again, this is generally an input to other planning studies that helps you inform your decision making. All right, disaggregation techniques. Proportional is kind of the classic one. This is, I've got X percentage of my load is here, so they're going to get X percentage of the new growth, or X percentage of my customer count is over here, so they get X percentage of the new growth. There's various different ways to do it, but they're all kind of in the same flavor. Propensity models is another one. If you have this data, like customer-specific likelihood of adoption, you can use that to disaggregate and allocate different forecasts to kind of get that locational granularity. And then kind of the adoption models are, again, kind of just a rolled up version of that. NREL does have a tool called the DGen tool that models individual customer level agency in terms of decision making at that very, very granular level. It's a really useful tool. It is generally pretty complicated, so it benefits from, it's publicly available, but generally benefits from somebody with some coding knowledge and some of the finer pieces. So it can be used, but it's a little more hands-on. All right. And duration, we talked a little bit about short-term forecasting. 0 to 3 years is generally what problems do I have now that I like immediately need to invest in. 3 to 5 years, 3 to 10 years is more forward-looking of here's what's in my forecast to start identifying mitigation projects for, identifying specific investments, start doing the justification. Beyond that, past the 10 years, you're looking out at things like aligning with 2030 clean energy targets, as an example, or 2050 non-zero, things that are like further out, a little bit more aspirational or a little bit more strategic. Temporal impact, I mentioned before, is a really important aspect of this. The actual load and generation profile makes a really big difference in terms of how it actually impacts the system. So the graphs that I have here are for different EV charging control and incentive schemes. And you can see how big of a difference some of these can be when they charge makes a huge impact. If my feeder peaks at 6 p.m. and all of my new EV charging load is also coming online at 6 p.m., I'm going to need a lot more capacity to deal with it. If I can shift that out flatten it out or move it to the morning or to overnight, I may have the same number of EVs, but the actual impact to my distribution system could be a lot smaller. Yeah.
Quick question, is this an output from that engine?
No, this is taken from a 2019 DOE report. It's a little dated at this point, but
It
it's,
wasn't used by the DG.
no, it wasn't. The profiles are complicated. It depends a lot on rates, incentives, customer behavior, charging availability, lots of factors. But trying to account for it is really important. Yep. And then this all culminates in kind of this scenario modeling, right? So you have a lot of decisions, you have multiple different types of resources. Scenario modeling is a way to look at some what ifs branching off of kind of where you start. So you may want to look at what if I have high levels of EV adoption, higher than my baseline, or higher PV, or put them together? What if I add an incentive? What if I add a rate change to EVs? How does that impact my planning and my forecasting? Scenario analysis is that process. So usually you're establishing a baseline and then making different changes to see what comes out of your forecast, what mitigations you might need, how much you may need to spend under some of these different scenarios. All right, so that's DER forecasting in a nutshell. The next piece we're going to move on to is hosting capacity analysis, which is a passion project for me. This is one of the early projects that I worked on that I really got into the system level. Hosting capacity fundamentally is the amount of DER that you can interconnect without having to make major modifications to the system. Basically, with what I have right now, how much can I put at a given location before stuff starts to break and it starts to become expensive, before new construction becomes necessary. Usually in evaluating hosting capacity, you're looking at some specific constraints against a specific technology. So when I add PV, right, how much do I add before I hit the thermal limit of my conductor? Before I start to see over voltages to customers? Before I start to see reverse flow through equipment that's not set up for it? Or where I start to have like protection related concerns. That's kind of what hosting capacity is, and what the map kind of generates is this location specific data that says right here you can plug in this amount before stuff starts to break. Usually represented as a map. It can also be a tabular. In some cases that's better. In some cases maybe not. It's a little bit easier to develop. It tends to be at the substation level. Tabular data is really good if you don't really care where you have to go. If you want to just look for good sites, tabular data is really easy because you can just sort through Excel sheets rather than having to click through the map. So there's a lot that can be beneficial about different forms of this data. One thing I would keep in mind anytime you're looking at hosting capacity data, this is an analysis of the whole system. You're not getting the circuit level zoomed in engineer working on it model and results that you do for an interconnection study. There are some trade-offs to scale that can make this data less trustworthy than like an actual interconnection study. So there's always some caveats. There's always a little bit of potential for underlying issues, discrepancies that are really important to try to get out in front of and kind of fix over time. Use cases for hosting capacity. The first and the most prominent one is as a development guide for developers trying to find good sites, right? Having information about how much I can connect at a given location helps developers know what to expect when they interconnect, helps them to find locations where they can get land, where they can understand like, all right, here's a good site, interconnection costs likely to be low versus the alternative. Two other use cases that are prominent are kind of as a part of the technical screen. If you know where your limits are for hosting capacity, you can use that in the screening process to help kind of streamline some of the decision making for applications. And you can also use it as a planning tool, right? Knowing where you have constraints is the first step to solving those constraints. Okay, so use case number one, efficient project siting. Really the goal of this is to reduce the number of non-viable applications that come in or that are submitted by the developer. This has benefits to both sides. On the developer side, there's equipment, application fees, process. Knowing that you're at a site that's probably going to go through is always beneficial, cuts down on the cost and the amount of time it takes for you to get your project through. If you start at a good site, everything goes a lot smoother. On the utility side, dealing with bad applications is an order of magnitude more difficult. You have to, generally when you're doing the study, you're trying to identify what would it take to provide service here for this size. And that can mean going through large changes or new substations or lots of different alternatives to try to solve a problem. If you don't have any problems, it's a lot more straightforward, a lot less analysis time, and it's a lot easier to manage the queue if you don't have as many applications. So these are all really kind of important pieces of the value of hosting capacity. I have some good examples on here. There's a pretty wide range. On one end, you get maps that have a little bit of data, enough to kind of know some things, right? The calculated hosting capacity value, maybe the voltage. On the other side, in some cases, you can get very detailed like load and generation profile, all the different types of constraints available. Generally, the more information that's out there, the easier it is to use. But it's not, there's kind of a balance in what's available and how much it costs. And we'll talk about that in a minute. So types of information available: substation, locational, and hosting capacity, like calculations. At this substation, I have this much voltage, this like base operating voltage, and generally accommodating X, Y, and Z things. Maybe if you have protection, like 3v0, it can be on there. Feeder level data is kind of the same thing, right? What the equipment is, three-phase versus single-phase, overhead versus underground, load and generation profiles. An important one that I wanted to flag is the amount of DER that's connected and the amount that's in queue. This doesn't show up always in the analysis, but can be added on. If you're a developer and you know that there's 10 megawatts in the queue ahead of you on a feeder, that's a really important piece of information, right? So having that helps to make this a more useful part of the map. So as I mentioned, there's a lot of design decisions and trade-offs and kind of back and forth between the cost to develop the map, the amount of information provided, and the benefits to the developer. Some common ones are, how often do you update it, right? Annually is common. Faster than that is often useful. Sometimes some data, annual is fine, but for like queued generation, annual doesn't really give you much, right? So there's some specific decision making in there. Level of granularity, usually you want to be more zoomed in because you get better understanding of what's going on at a specific site. If your like block covers 100 square miles, it's really hard to know much. More information provided, like on the constraints on the load profiles, again, is generally more useful, but can come at additional costs on the development side for the utilities. Cost burden, really important. And then I mentioned the tabular format as well. Different benefits to tabular versus maps. All right. All right, so we're going to move on to the other uses for host. Oh, record? What? Oh, okay. So the other two kind of use cases for this in the interconnection screening process, again, kind of knowing what your limits are can help you design better screens to accommodate new interconnections without having to run studies or without having to do more detailed analysis, right? If you know you've got 5 megawatts of capacity on a feeder and you get an application for 100 kW, you know that you're probably not going to have a limit, right? Designing a better process around this is a really useful way to kind of build off of this. One example, I think it's a Pepco example in DC, but there is an area where a feeder can accommodate a certain amount regardless of where it is. Beyond that, you can kind of add some additional, if it's in the right locations, if it's close to the substation or close to the load, and there's a line beyond which it doesn't really matter where you put it, you're going to start to see issues, right? So this is a stochastic analysis because obviously it could be located in a bunch of different locations. But knowing, all right, I can get this much on this feeder or like up to this much, but not beyond that, can again help you design a better screening process. And then finally, use as a distribution planning tool. People are a lot more engaged in planning for new hosting capacity In some cases, commissions have ordered utilities to start making investments to make hosting capacity available. And again, knowing where those constraints are can help you target specific areas to make improvements. Again, as long as you can also get land and the permitting and some of the other pieces as well, that has to be a part of it. But this is an important input to that process. This was an example in HECO where they're using kind of the same type of approach. I can connect this much. My forecasted PV growth is X. I can accommodate this without upgrades, or I need upgrades, or I need big upgrades as part of the planning process related to DER are kind of rolled into that forecast. Okay, so last but not least, non-wires alternatives, the solutioning part of DER planning. Non-wires alternative is a sort of non-traditional way to use DER as a resource to defer or replace investments in energy delivery equipment that would otherwise be necessary, so long as it is cost effective, right? And that's a key piece. When we talk about NWAs, there's really 3 applications at the distribution level that are the most critical. First is capacity. This is probably the most common one. This is injecting power or reducing demand to get more capacity out of existing resources where you have a constraint. This is, I need a megawatt at peak so that I don't overload my transformer. Reliability is another really common one. This is the ability to provide an alternate source if you lose the primary source. So a home generator is a sort of non-wires alternative. And this can be done at the circuit level scale or the substation level scale as well, kind of the same concept, right? If you lose your source coming into a substation, you can provide another source using DER. And then finally, voltage support. It's a lot less common just because voltage solutions tend to be a lot more cost effective. Cat banks are pretty cheap, but you can use DER to help solve some of the voltage related issues that would otherwise require investment. When we talk about these, there are kind of 3 different levels of granularity when you're talking to NWA procurement. First, system level initiatives that don't really have a lot of specific like locational pieces, but generally encourage development of DER to help reduce demand or improve efficiency. So like net metering is a good example, right? You're encouraging more DER kind of everywhere. By just the odds, some of that's going to go in places where you're going to experience constraints where that capacity is going to be useful. It's not geo-targeted, but it's there and it's kind of having a benefit. The next level down is more geographically targeted, but not at the specific level. So when we talk geo-targeting, this is tailoring programs and incentives to specific areas, but not necessarily all the way down to this technology of this size at this location. The value of DER is a big one of these, where you're generally kind of incentivizing new installations in areas that have value far enough in advance that you can kind of realize that and not have to make investments. And then finally, specific grid needs are like the most common examples. This is, I need X number of megawatts of Y technology at Z site, right? Everything's pretty nailed down. I know when I'm going to need it. I am procuring a specific solution for a specific problem. Microgrid for reliability is one good example. Okay, so when we talk about geo-targeting, this is, again, a kind of a proactive approach to providing, kind of casting a wide net in an area that you expect to need reinforcement. So when I was a planner, I had one specific town that was served by 4 different substations. I knew I was going to have a lot of growth there. I didn't know which substation it was going to land on, right? It could be in this part of town, it could be over there, it could be in the south part of town. I don't know which one I'm going to need first, but if I can target that area for energy efficiency or for incentives for value of DER, I can help defer the need for upgrades. That's kind of what we're talking about with geo-targeting. You want to use what you know to help guide and influence decision-making for other investments and programs to help provide capacity. helps to optimize local resources. It's a lot more scalable and tends to be flexible, right? I don't necessarily need to buy 8 megawatts of new capacity if I only need half a megawatt. And again, can help defer that capital expenditure. The classic example for NWAs is Brooklyn Queens Demand Project in New York. I don't want to dwell too much on this one because everybody who's ever presented on NWAs has this slide somewhere in their deck. But I think the most salient point is that it's still going, right? This wasn't a one and done in 2014. This is still going. It's still being reported on, and it's still providing that savings in this area. Initially, I think it was $1 billion investment that was avoided with $200 million worth of DER. Again, this is still going on today. 61 megawatts of load relief in Q2 of 2023. So it's still providing, it's still producing, and about half of that was from energy efficiency, which is a huge benefit for customers, pretty obviously. A less talked about example for NWAs, also in New York, Central Hudson has a peak perks project that is reducing demand for air conditioners, either using smart thermostats or direct load control devices, like on the time of peak, with the goal of reducing T&D needs for 3 specific areas that would otherwise require investments. Again, this is kind of summer peaking. It's a voluntary program that they're enrolling customers in, where they get a rebate, and there's a performance component also. Every year that they're signed up for it, the utility can either adjust the set point on the thermostat or trigger the load control device to shut the air conditioner off at peak during these really congested hours. And again, they get an initial enrollment bonus and then an annual incentive for that resource being available. Overall strategy, again, reduce peak demand, not have to make capacity upgrades in T&D infrastructure, and instead kind of pay customers for having that resource availability instead of putting it into classic infrastructure. In terms of outcomes, the first year of the program, they met all 3 of their targets. They had about 5.9 megawatts of load reduction compared to a 5.3 megawatt target. So very successful program, met the deferral need and actually continues to be successful in preventing that investment from becoming necessary. Another example that's more reliability focused, that's close to my own heart from Illinois, is the Thebes battery that's in Ameren, Illinois territory. This one is a 1 megawatt, 4 megawatt hour battery deployed to serve a very small town in the very southern end of Illinois that is supplied by a radial line that runs through the Mark Twain National Forest. So lots of reliability issues, lots of issues trying to trim trees, very far from any additional source. I think the estimate was in the tens of millions of dollars to run them another supply to about 200 customers. So the economics of traditional solutions, not great. In comes battery storage, right? I drop my new source in town. Whenever I lose that primary supply, the battery stands up and turns on and supplies the town until the original infrastructure can be restored. This turned a worse performing circuit into a much more reliable circuit for a lot less money than it would have taken otherwise. So the folks in town there have been really liking the battery. Again, fewer and shorter outages with generally really positive feedback for a lot lower price. So one of the big pieces of non-wired alternatives is figuring out when it's going to be useful and when it's going to be valuable and when it's actually cost beneficial. There's a lot of approaches to this. Generally, they roll in a bunch of different factors, things like capital cost, time to implement, flexibility, reliability benefits. Usually there's a screening process. It's like these are the set of projects that are traditional that may be benefited or may have an NWA that competes, and they kind of go through this analysis process that way. Cost benefit evaluation is one of the biggest pieces. So usually you have a distribution component to avoided capital cost or reliability improvement, but you also have the ability to realize other benefits in transmission and energy generation when you don't need it for distribution. So considering all of the pieces of that value stack are really important, and actually considering it for all the things it can do. When you're looking at multiple value streams, it's also important to make sure you can actually achieve all of those at the same time. If you're planning on using your battery for reserve capacity for distribution, you can't also bid it into the ancillary services market because you may not have it available when you need it, right? So managing these commitments is a really important part of actually considering the value completely. When we talk procurement mechanisms, there's really kind of three pieces. First, specific grid needs, direct procurement. This is, I need this battery of this size at this location, and I'm going to go out and buy it, and I'm going to own it, and I'm going to operate it. There are some business model limitations for deregulated utilities, but this is usually kind of the simplest approach. Specific grid needs, distribution services approach is more along the lines of, hey, I need this much capacity at these times a year, and I'm going to contract a resource, and the rest of the year, I don't care, do what you want. This is, I need this service when I need it, and otherwise, we're kind of free to get whatever value that you can squeeze out of it. And then finally, geo-targeting, programmatic level, we talked about previously. Classic example for distribution grid services approach is in California. The Distribution Investment Deferral Framework puts out a solicitation that says, I need 5 megawatts at this location. I'm going to call it this many times a year during these hours, during these months, and they get responses for like an RFP. A less commonly shown one is this one in Colorado, which is very similar, has the same kind of general structure. This was an RFP that went out earlier this year. Unfortunately, they got 0 responses. There's also a report kind of post-mortem for this process for what improvements can be made to help get developers to respond to some of these. So there's a lot of kind of ongoing best practices and refinement in the NWA space, kind of helping to make these practical and achievable in real terms. And then finally, geo-targeting, value of DER. New York has their VETR tariff that is trying to compensate DER for the value that it provides in a location-specific way. So if I am on a feeder that has a capacity constraint and I install solar and it provides capacity, I would get compensated for my benefits that I provide to the grid. It's a way of directing private investment into areas of grid need, which has a lot of potential positives. So in closing, we covered a pretty wide set of topics. There's a lot of different questions that you can ask utilities to kind of dive into what they're doing with each one of these, how they're making decisions, and kind of what they're using these pieces for.